you missed one line in my bio, which is I've got 45 years of experience, which was going to be my trigger for coming up here and saying, because it's the first thing after lunch, I wanted to stir things up a little bit. And I was thinking about that and realizing that I probably spent 70 to 80% of my career during that time working on issues that, if not directly related to stormwater, or at least closely related to stormwater. And that makes me reflect and think that you know, Jeff Foxworthy was recently in Worcester, I think, and I didn't get to see him, but I always like his little line, you know you're a redneck if, well, here, this is, you know you're a stormwater nerd if you've spent over 50,000 hours of your working career on stormwater. Or you know you're a stormwater nerd if you actually made that calculation. I hate to tell you this, you know you're a stormwater nerd if you spent an entire workday in March talking about stormwater. You know you're a stormwater nerd if you look at Nick or at Matt in the middle of a project and say, is this the project where we're going to make stormwater run uphill? Or how about the solution, this solution, let's put the rainfall back in the air. Ooh, there's an idea. So for the next 20 minutes, I'm going to talk about putting rainfall back in the air. And I need the clicker. You didn't give me the clicker. So, trees intercept stormwater. It evaporates from the leaves. Does that have a role in our stormwater management? Can it have a role in our stormwater management? Is there a nexus there to help us in our stormwater, in controlling stormwater in development projects and in addressing our MS4 projects? That question intrigued us, and so we elected to look into it. And so I'm going to talk to you a little bit today about these topics. Are there runoff reduction benefits from tree canopy, and if so, how can we quantify them and implement them as part of our stormwater program? How do we do that through the MS4 program? Is there a nexus there or is there not? And if there's some time at the end, we'll talk a little bit about the context of this in terms of some safety considerations and nutrient management considerations, other things that might come into play. In 2007, this Center for Urban Forestry Research did an inventory in New York City, and this has been done in a number of cities around the country, so you can go and look these up on the internet if you wish. But this intrigued me a few years back. They did an analysis of the contribution of various benefits of tree canopy to the welfare of the city. And they actually were able to quantify these benefits by some formulas and by looking at the costs that they were expending on things like stormwater, and came up with some really interesting results. And what they did was they came to the conclusion that based on the 2007 dollars, I would say, about $122 million worth of benefits were provided by the many hundreds of thousands of trees in New York City. About 25% of that was savings in treating stormwater. And they concluded that on average, they were saving 1,400 plus gallons per tree per year in stormwater costs just by having tree canopy overhanging pavement. That intrigued us, so I went online and started looking at some utilities that I found that have been assembled by the U.S. Forest Service and Arbor Day Foundation and other partners. There was a tree calculator, and it was set up by region, so you could look at sort of the Northeast had an index tree someplace in Queens, New York, and this index site. You could pick a tree and a tree size and figure out what its benefit is, and by golly, a 12-inch red maple, when you ran through their little utility, showed that you could save 1,300 plus gallons per year on storm, on runoff, quantity of runoff just by having that tree. In the annual rainfall basis, that's almost 10% of annual rainfall that's falling on the footprint of that tree. So it seemed to us that there might be a benefit to having trees incorporated into the landscape, especially when you stop and think about the fact that on a typical development, we cut down several acres of trees to build facilities, whatever they are, and then we cut down or clear another patch of land to install a detention basin to make up for the fact that we cut down all these trees. And there seemed to be a little bit of irony in that activity. Why are we removing these tremendous pumps to put in stormwater treatment? Do these have a role in the overall scheme of things? So we wanted to look into that. I don't know if you can see it from the back of the room, but if you go out early in a rainstorm and get to the right vantage point, it's pretty telling. The drip line of the tree is quite obvious there, and you can see it ground level here, the drip line of the tree. It stays dry in that pavement for some period between the onset of the storm and the onset of runoff. And what you're doing is you're saving up storage capacity in the pavement for later in the storm. When the storm really gets pelting, you're not saving much. It's not going to do anything for peak rate control, but there's some extraction of runoff volume early in the storm and in small storms that could be significant if you totaled across the period of an entire year. So what we did was we proposed to the MassDEP 319 funded project to look at whether trees have a benefit and could be used in proximity to pavement to offset some of the runoff that you end up having to collect over the period of a year. And if so, could we build that in, build some credits around it or some incentives to take advantage of this benefit of something that we like to have in the landscape anyway. And so we looked a little deeper at some of the utilities and software available, and again, the USDA Forest Service, in concert with a number of partners that are involved with the management of urban forests, if you will, have put together a set of software and related tools called iTree tools. And in that package is a software package called iTree Hydro, which is a fairly robust hydrologic program that takes into account pretty much all components of a hydrologic cycle above ground, at ground, and below ground, and enables you to take landscape scale view of an area of interest and determine what tree, how the stream system is responding to the quantity of trees on the landscape. And we fiddled with that model a little bit to make it, to bring it down to a very small landscape scale and look at some representative site scenarios before and after, without trees and with trees, what the trees' impact was on the runoff from the paved surface. And so we're taking this situation, comparing it to this situation, and some hopefully realistic design scenarios so that we could quantify what the effect of the trees was. The model enables you to look at various, I don't expect you to read this because I can't even standing next to it. But what it does is it gives you a sort of a spreadsheet format with different aspects of the hydrologic cycle represented in an aggregate way for annual runoff, for instance, annual evapotranspiration. And it also has some sub-utilities to look at individual pollutants. In this case, we looked at phosphorus loading. So we ran through some scenarios using this model and these outputs to see what would happen. For scenarios, we took the MAPC, the Massachusetts, the Metropolitan Area Planning Council has I think it was, developed a guidance for basically environmentally friendly site design road standards. We used some of their road design scenarios and we populated them with trees at various intensities, if you will. Large trees on one side, with the other side's got utilities on the road or something you wouldn't be able to put trees. Smaller trees on both sides, big trees on both sides, just to get an idea of the range. And we spaced these, basically what we did was we pulled out just random subdivision ordinances, looked at what they required for tree plantings along the road corridor in a standard subdivision, and planted the trees at those intervals and just varied their sizes and the number on each side. And at the bottom, we total up how much of the pavement, how much area is covered by tree canopy in these scenarios when the trees reach 40 years of age, and then how much pavement is under that. So you can see from this, if you can read the figures, that we range from 40 to 80% area beneath the tree canopy as a proportion of the right-of-way, and pavement beneath canopy varies from 30 to 70%. So not an unrealistic scenario to get someplace in excess of 50% of canopy coverage over pavement along a standard subdivision road designed according to MAPC guidelines. We did a similar thing with an urban street, a 60-foot right-of-way, trees at the corners only, small trees on both sides, large trees on both sides, tallied up just what's within the right-of-way and beneath the tree, and up to 53% coverage. So a significant amount of canopy overhang if you can get these things to maturity, if. We'll talk about that later on. And then a typical parking lot. And interestingly, I looked at some, again, a random sampling of communities that we've worked with in the past. And a common design criteria for a commercial parking lot is to try to achieve 30% tree canopy coverage. And that seems realistic given what we have here, ranging from 11% if you just trim the edges of the parking lot with trees, but 38% tree canopy total, and 26% of it pavement if you get trees every other, basically double-loaded parking bays separated by trees and a 10 or 8, 10, 12-foot island. So again, all of these scenarios, you're getting someplace upwards, you can get someplace upwards of 25, 30% or more in tree coverage without having onerous landscaping requirements compared to what we typically have in our regulations. Then we started looking at, by looking at how the model is set up and sort of tinkering the parameters of each of these landscape scenarios to normalize them to 1 square kilometer or 1 acre or whatever. So we're comparing each one on similar parameters. At the tail end of all this complicated process of doing a model, we came to the conclusion that in Marlborough, Massachusetts, you can expect that for any square foot of pavement that has leaves over it, you're going to get a 15% reduction in annual runoff. And it varies a little bit with where you go in the state and the location because of the variation in rainfall and the rainfall pattern and intensity. Trees intercept a small amount at the beginning of a storm, or they intercept small storms. We talk about the first flush in stormwater runoff. This is like the first drip. But nevertheless, it's basically it's 15% of the first flush is what we're talking about here. Some variation depending on where you are, some variation with a type of tree, but 15% seems like a fair and reasonable figure given the overall precision with which we can analyze rainfall events over long periods of time. And then the other thing we're looking at, I keep saying the canopy overhanging the pavement. There's 2 reasons why I keep saying that. One is that the EPA regulations, the DEP regulations, most local regulations are based on a treatment standard that is equal to some factor times impervious area, or times connected impervious area. We're always treating runoff from impervious area. So we were looking for modeling this in a way that we can index it to that treatment standard. We're treating from impervious area. We don't require treatment of pervious surfaces, or we don't count it as we size our system. So we're indexing our approach to the regulatory approach, which deals with paved surface. The other thing is if you look at these small storms, the amount intercepted by the tree and protecting up to the level where it's protecting against runoff from pavement would happen even if the tree wasn't there. Grass, shrubs, whatever, would be able to intercept the same amount of rainfall in those small storms. The disadvantage of shrubs and grass is that they don't overhang pavement. Trees do. And some trees do if you're going to use them as part of your stormwater management system, because you're not going to plant a conifer here with a shape like this, because you would have to come and limb up the branches that are doing the work, and they wouldn't be providing you any benefit. So the thrust of this study was to look at, is there a benefit? Yes, there is. Is it really big? It's not really big, but if you're talking about the new MS4 standards, for instance, which are requiring retaining 1 inch of runoff, that 1 inch could become a little less onerous if you could take 15% of it off the front end by having the tree overhanging the pavement and catching the rainfall and letting it evaporate back for those small and the beginning of the storm. So it's, you know, a lot of our stormwater design work is working with a whole bunch of different measures to try to make the job easier for us in the end to treat what's left. So we would count this along with pavement disconnection, which is directing your flow onto qualifying pervious areas where it can infiltrate, and other low impact development devices and strategies in your toolkit to bring the total volume of stormwater down that you need to use high intensity BMPs and expensive BMPs to treat. So every little bit helps. Can we get 15% off the front end by letting trees overhang our pavements and providing incentives to do that? Keep existing trees, plant new trees. So we're looking at this 1 inch or the 0.8 inch for redevelopment as our sort of the threshold that we're going to try to bring down and provide developers or communities with incentives to keep or plant new trees to make their job easier when it comes to designing the BMPs that they're eventually going to need. As part of this project, we are developing and have drafted, and I'll tell you where to find it in a moment, some regulatory language that would enable you to build credits for developments into the process by preserving existing trees that can overhang pavement, providing new trees that can overhang pavement, and providing for long-term viability, which means you got to pick the right tree, you got to plant it correctly with the correct amount of soil to support it, and you've got to have some method there to maintain it and replace it if you need to over the design life that you're expecting it to perform. Existing tree. We have this thing called the critical root zone, which extends at least as far as a tree canopy and sometimes further. Best to have an urban forester or an arborist advise you on individual trees, but generally we're going to stay out of the drip line and sometimes some distance outside to protect an existing tree. So the problem with keeping new trees in the landscape is not trespassing further into this critical root zone that already happens. The plus side is I've worked on some roadway reconstruction projects, for instance, where there's a considerable number of urban trees overhanging a pavement, and if we can correct the root damage problems that have occurred over a period of time, lifting sidewalks and so on, you already have pavement trespassing beneath the tree, so you don't have to worry about that component on the root zone quite so much. It's just if you have a tree out in the middle of a field and you're going to build pavement around it, you're going to have some limitations. That has to be built into the regulatory and just the design process. How do you protect a tree from the pavement? And then with new trees, you're not going to plant a 40-year-old tree as a part of the project normally. I imagine it's been done. You're going to plant a 2-inch caliper, 2.5-inch caliper tree. it's going to have no benefit for a while because none of it's, it's going to be some distance from the curb. None of it's going to be providing any shading over the pavement. That's going to come about 40 years down the road. We did look at a variety of trees used in Massachusetts and how they change with age. And it's, again, it's not there's not a lot of precision here, but roughly, if you take what it's providing as a benefit at 40 years old and the benefit when you put it in, the day you put it in, and sum those two together and divide them by 2, you have a good representative of the average benefit of the tree. So we suggest if the full tree would give you 15% reduction and you plant it as a small tree, well, we'll only credit it for 7.5. So there we are, existing trees, you get 15% volume reduction for any canopy that overhangs the pavement, but you need to protect it during construction, and you can't destroy the tree by building pavement under it by willy-nilly building pavement under it. You need to do so with professional advice. New trees, 7.5% volume reduction because it takes a period of time to get enough canopy to give you the benefit. A big thing is going to be providing soils of adequate volume to support the growth of the tree. And in all cases, we need maintenance or replacement, care for the tree. You may need to have some form of surety or a tree program that ensures it's going to be there. I'm going to come back to this canopy versus pavement relationship. Two sides of the coin: will the tree destroy the pavement? Will the pavement destroy the tree? And this idea of tree canopy versus soil volume. Presumably, all these trees were planted at the same time. Look at the ones in the middle. They're in little teeny tree pits. The ones around the edge are in this nice wide landscape strip, lots of place for the roots to stretch out and to obtain the moisture and nutrients that the tree needs. There are ways to get those trees in the middle or to provide them with greater soil volume and access to this moisture and nutrient. But it wasn't done here. But this is what happens if you don't. And what happens is these trees in the middle will reach a certain canopy diameter and they'll just cease to thrive and possibly even die. And as a matter of fact, there's statistics indicate that the average life of a tree in an urban setting is 7 to 10 years. And the primary reason is because it does not have a place where the roots can extend to mimic the drip line of the tree. The rule of thumb is you need 2 cubic feet of soil volume for every square foot of canopy footprint that you have. And when you do that calculation, a 4x4 foot tree pit is just not going to do the job. You need something more like an 8 by whatever the spacing between trees is, tree pit, 30 feet. It's like 250, 350 cubic feet soil volume. So you need to provide for that as part of the installation of the tree, or you might as well seek another BMP. Read into that if somebody's proposing a tree box with a bottom on it as a treatment mechanism, you've got about 10 to 12 years worth of tree growth to depend on in that. Plan on replacing it or plan on another BMP, because you need the roots to have some place to go without destroying your pavement. There are ways to do this beneath pavement using pavement, basically suspending the pavement on some kind of structural system that allows the roots to penetrate without destroying the pavement. There are proprietary soils mixes that can be done, or you can simply provide decent linear landscaping islands, for instance, in parking lots or on the verge of pavements that allow for the soil volume. It doesn't have to be circular or whatever, it just has to be there in some direction. So we've developed some ordinance language to build this in that includes these provisions: prevention of future removal, replacement as you need, maintenance as you need, and then because you're going to lose the leaves, and we're talking in many cases about dealing with phosphorus, we don't want that phosphorus sitting in the gutter to be washed into the gutter after you've taken all the trouble to take it out of the system, so you have to have it coupled with a street cleaning program that's appropriate. We've summarized this on a website that is now live, but you're going to get a number of story pages on it because we're still populating it. www.treecanopybmp.org. There's some postcards out back if you'd like to take a look at it. The ordinance language is there. There's links to other resources. There's tons of stuff if you want to develop a community tree program or explore ways to use your trees for stormwater management. And then the regulation is on the website. Our model regulation is on the website, or you can contact us and we'll give it to you. It's been designed to fit with the MAPC's model subdivision or stormwater bylaw that they are currently updating and tell me will be available late spring, early summer that incorporate the provisions of the new MS4. And this has language in it for selecting the trees to conform to your tree list and maintenance and the sizing and the soil volume and so on. And then if you're interested in even going further and exploring community tree program, there's resources through iTree Tools. There's resources through us consultants that can assist with GIS, canopy mapping, for instance. Another advertisement for our drone services. But basically, we can get high-resolution stuff to either inspect people's tree installations or to figure out what we have as a resource. Josephine tells me we can train, or we're working on training our software to be able to automate recognition of trees as part of this mapping effort to make it really easy and simple to do. And then just very quickly, safety is a concern. This is context sensitive. Depending on the road, you may not want trees right next to the road. Take a close look. And I've already talked about the nutrient management issue. We need to attend to the collection of phosphorus that we've accomplished by this BMP. And that's my story.